how does the Great Orthonormality Theorem comes from these two simple rules that average of a constant is a constant and average of any non-trivial vector that all components rotate is 0. Consider something that depends on components of X in this form, xi, xj. If you average over this, what's going to happen? I can write this I prime, Kronecker delta of j prime. And whenever index appears, take this term one over dimension of the space where xi, so xi e. And as there are lots of such vector spaces, you will actually give them a label, and this will mean it will be irreducible representation. Meaning when you rotate this vector, all components rotate. There is no subspace that just sits there, like zx is rotation around zx. But here I'll omit this new index for a while. But now I can write this j into indices I prime and j prime. It has 4 indices. And p is over d delta. But this I can write as my projection operator ij acting indices plus 1 over d. When I contract these guys here, I just get x squared and 2 extra indices that come along for a ride. You'll usually see this, one possible word to say is that you decompose a matrix with 2 indices. This xij you can think of as a matrix. So if I identify 2 indices, sum over it, I'll get x squared in Euclidean norm. This object is what remains when I remove the trace. So this is an example of a non-trivial representation. I started with irreducible representation, but I took several copies of it. And then I split it into a part in which the action of the group is that this just rotates. An average, group average, x squared over the dimension of the group. Now various three-dimensional discrete groups that happen in crystallography are that's called Schur's lemma. So now x I belongs to representation U, space of dimension, in general of different dimension of t. Then, if I look at x in U of j, and I average over the group action, I cannot form a singlet because I cannot dot 2 different representations. So I find out that this can give me the result only in which case this combination does contain trace part. Then we can look at what this averaging really means. Now, what this averaging really means is when I tell you that I'm taking xi, xj, I'm averaging over a matrix with x on the first guy. Depends on the group element. Put indices of representations, nu and nu, and the dimension of the representation. And then there'll be I deltas you have to insert here. And if you just fill it out, that's all. The Great Orthogonality formula. So it just comes from this very elementary consideration.